Hello everyone, in this video I'm going to explain a common problem that data scientists and machine learning engineers face when they are training machine learning models. And this is also a common interview question, so maybe this video could be interesting for those who are interested in applying for data scientists or machine learning engineering jobs. So the problem is about the difference between bias and variance. And what does the bias-variance trade-off mean? So I'm going to explain these concepts using a small example so we can have a better picture of these concepts. So let's imagine that we perform an experiment and we collect some data points and we decided to plot these data points. Our job as a data scientist is to find a model that captures the behavior of this data set. Ideally, we could like to have a mathematical formula that represents the behavior of this data set. Let's say that the behavior is of this hypothetical formula is something like this. So this black line is able to capture the real behavior, the true behavior of this data set, right? Now let's split our data set into two data sets, the training data set and the testing data set. Um, and let's use two algorithms. And these two algorithms will represent two cases. In the first one, let's train a linear regression model to fit this data. Let's say this linear regression model is something like this. I represented the linear regression model as a straight line, straight red line. So we have here our model. As we can see, this model, the straight line, is unable to capture the true behavior of our data set because you know, as maybe many of you could know, a linear model cannot represent this curve behavior or this curve behavior. So this model has errors when we try to for example, measure the difference between the data points and the actual model. We find that this model errors have errors. So this inability of the model to capture the true behavior of our dataset is called bias. Since this model is unable to represent the curved behavior of this data, we call the or we say that this model has a relatively high bias. Now let's try with another algorithm, and let's use the color orange to represent this model. This model, let's use maybe green, no, blue color, the blue. Let's use blue to print this model. So this model looks like this. So as we can see, the blue model can capture the behavior of each data point in our data set. For that reason, we say that this model has a really low bias, almost zero. Now, this case is also called overfitting because in this case our model is memorizing each data point in this data set. So let's compare these models using our testing data. So when it comes to testing data, as you know, this is data that the model has never seen. So we notice that the the straight line has errors. Yes, as the case with the training data. So we have errors, and for that reason we say that this model have low variance, because variance is the difference between the performance with the training data and the testing data, or in other words, is the performance when we change the data set. In this case, we notice that the behavior of the straight line remains similar in both cases, using the training dataset and the testing dataset. Now, if we try to measure the errors using our blue model, we can see that now this model has errors, but before it hasn't. So we say we say that this model has high variance because the performance, when we change the dataset, also changed. So before, with the training dataset, the error of our model was almost zero, but right now when it comes to testing data, I mean data points that the model has never seen, uh, we can see errors. So this model has high variance. Um, this is one characteristic of overfitting models. They perform really well on the training data set, but really bad when we are using the testing data. On the other hand, the straight line that represents the simple model is a case of underfitting, um, meaning that the model maybe is too simple and is unable to capture the data set, the behavior of the data set. So in this case, we can notice this underfitting. For example, in this case, this is even more difficult to detect, but we say that is underfitting when have high bias and high bias and high variance. So let's use another image. Let's use this image. Here we have three cases. The first one, at the left, we have our overfitting model, right? Our model memorized each point in our data set. So it has high variance because if we train this model, if we test this model using testing data, we are going to see that this model has a relatively low error rate. On the other hand, we have in the middle the model that represents a high bias case. So in this scenario, the straight line is unable to capture the true behavior of data. This model is just too simple to represent our data set. So we call this an underfitting situation, and it has high bias. Finally, we have a model that represents our ideal case. Low bias, meaning that it's able to capture the general behavior of our dataset, and low variance, meaning that this relatively well performance that it got using the training data remains similar when it comes to testing data. So what we call trade-off is this sweet spot between a simple model and a complex model, a model that is able to represent or to capture the general behavior of our dataset, training dataset, without paying too much attention to particular cases, like in the overfitting case. So what is the thing that we call trade-off? So maybe the next videos, in the following videos, I'm going to elaborate more about some techniques that we can use to prevent these kind of problems. So this is all for now, and thank you for listening to me, and goodbye.